We want to investigate the extrema for functions of two variables. The extreme value theorem is not anything we will actually be using. We won't be proving it either. However, all it says is if we have a continuous function defined on a closed bounded region, then we've got to have minimum and maximum values. Now here is the definition for local maximum. Notice I've drawn a picture of this for you. So basically what it says is if you have a region in your XY plane, a circle in the XY plane, then if there's a point on the surface whose X and Y coordinates are in that circle, if the Z value for that is the largest within that circle, then it's a maximum. Similarly, the definition for local minimum is that if you've got a circular region in your XY plane and you've got a point whose Z value is the least of any value in that circular region, then that's your local minimum. In an earlier section, we talked about the equations of the tangent plane. Here's our computation for the equation of a tangent plane. Notice that if the partial of x is 0, that means the slope in the x direction is 0. That means we have a horizontal tangent line in that direction. And if the partial of y is 0, then we get z minus z naught equals 0, which is a horizontal tangent plane. The key to this is, of course, that. And here's just a pictorial version of what we just said. The slope in the x direction and the slope in the y direction have to both be 0. And so here is our definition for critical points. And this is basically our computational technique. If we have the partial of x, the partial of y that are both equal to 0, then we have a critical point. We also have critical points where either the partial of x or the partial of y are undefined. So let's see how those ideas play out with this function. I've drawn the graph of it simply for you to see that this particular function does indeed appear to have a minimum value. So we'll take the partial of x, set it equal to 0. We'll take the partial of y, set it equal to 0. Now remember, these both have to occur. So we have to have x equals 1 and at the same time y equals 3. Well, and essentially that is our answer. We want the point x equals 1, y equals 3, or the point 1, 3. So that's our critical value. The function value at 1, 3 is 4. So now we'll check some values close to that critical point. Here's a little manipulation on the formula. Notice that the x minus 1 squared is always positive. Since you square a number, you get a positive. The y minus 3 squared is always positive. If you take a 4 and add some more positive numbers to it, the answer is going to have to be bigger than 4. That means our critical point is a local minimum, since all of the points around it have bigger values. So we'll go through the mechanics again. Here's a graph of z equals y squared minus x squared. I don't know if you can recognize this, but there's something here that's kind of special. It doesn't really look to me like it's a minimum or a maximum. However, we'll do the process on this. We'll take the partial with respect to x, set it equal to 0. We'll take the partial with respect to y, set it equal to 0. We want x equals 0 and at the same time y equals 0. That implies the only potential critical value is indeed 0, 0. We plug those in and we get a function value of 0. So now we need to know around the point 0, 0, do all the points have values bigger than 0 or smaller than 0? So let's take a look at values along the x-axis. So we're going to set y equals 0. And if y is equal to 0, we get just f equals negative x squared. Well, x squared is always positive, so a negative x squared is always negative. So in the x direction, from the point 0, 0, all of the answers are negative. However, if you look in the y direction, all of the answers are positive. Now what that tells us is there are some values near this critical value that are positive. There are some values that are negative. So it is neither a maximum nor a minimum. Now, as I pointed out in the graph at the beginning, the point that we just found was actually a minimum in one direction, but a maximum in another direction, and that's referred to as a saddle point. Now, rather than going through all of the computational things that I did on the previous 2 examples, we have something similar to what we did in Calculus 1 called the second derivative test. Here's how it works for functions of 2 variables. The idea is, if this is going to be a local maximum, then any vertical slice would have to have a maximum at the point PQ. If any vertical slice didn't have, then it wouldn't be a maximum. So that's sort of the idea. And here's the same thing said for minimums. So basically all that's saying is every vertical slice has to have maximum and minimum in order to be a maximum or minimum at the point. Now we did something like this in a previous section. If we've got any curve and a point PQ on that curve, then we can describe that curve in terms of the direction components. Our direction is going to be m and n. We're letting m be the direction in the x direction and n be the component in the y direction. So we can write the equation of any vertical curve in terms of z as some function of the x component and the y component at any point plus the directions with respect to t. So, if x is p plus m times t, then the derivative of x would be the derivative of p, which is 0, the derivative of mt, which is m. So we have m as the slope in the x direction and n as the slope in the y direction. Now, we're going to do the chain rule for dz dt. That would be the derivative of f with respect to x, dx dt. Well, dx dt is m. dy dt is n. So we'll replace those. And then we'll do the second derivative. So we're going to do the derivative of this. Okay? M is a constant. The derivative of f sub x is the derivative of f sub x with respect to t, and the derivative of f sub y with respect to t. Now, by the chain rule, the derivative of f sub x with respect to t is the derivative of f sub x with respect to x times dx dt. The derivative of f sub x with respect to y times dy dt. So that's how we get the derivative of f sub x with respect to t. Now all of that just means here's dx dt, which again is m. Here's dy dt, which is n. So let's replace all of those and then multiply that out. Now let's investigate that formula. So you notice that this is like the quadratic something times m squared, where the something is what we're calling a, something times mn, which is our b, and something times n squared, which is our c. So this is like a quadratic equation. And a quadratic equation, the m and the n have the same signs only if this b squared minus 4ac is less than 0. Now that should look a little bit familiar from back in college algebra. Now we're going to substitute for the b and the a and the c what we had up there. There's our a, b, and c. So plugging those in, this is what we get. Multiplying that out, multiplying both sides by negative 1/4. Remember, that changes the direction of the inequality. We end up with this. Now this expression is what we were after. Whether or not you understand all the calculations I did to get to here is another issue. But even if you don't, you need this expression. So this relationship is called the discriminant. The discriminant is usually abbreviated capital D. An easy way of remembering this formula is that it's a value of the determinant formed by the second partial of x, the mixed partial, and the second partial of y. Now here's what the second derivative test looks like. When you get this screen finished, you could print it off and have you a little chart that has all of the things on it that you need for the second derivative test. This is called our discriminant. Now, if the discriminant is positive, then we check the second partial of x. Now this should look a lot like calculus 1. If the second derivative is positive, then we have a local minimum. That was exactly the same second derivative test we learned in calculus 1. Only this time, notice, the discriminant has to be positive for that to work. Likewise, if the discriminant is positive and the second derivative is negative, then we have a local maximum. Now, if the discriminant is negative, it doesn't matter what the second derivative is, we're going to have a saddle point. So notice we've got situations that occur where the discriminant is positive or negative, and we can determine the nature of the critical values. However, if the discriminant is 0, then we don't know a blooming thing about it. So let's go through this example. I've already drawn the graph of this, and you can kind of see from the graph that we should come out with 2 local minimums. Can you recognize that? That is a saddle point. So I suspect I'm going to get 2 local minimums and a saddle point. So our computation is we do the partial of x, partial of y, set those equal to 0, and try solving. Well, that's about as far as we can get with that. We'll take the other one and set it equal to 0 and try solving. Now, we did this back in algebra. If we've got 2 equations with 2 variables, we can use the substitution method for solving them. Here we've got y equals x cubed. If we take the other equation, we can replace the y with x cubed. Now, that gives us an equation with just x's. We can finish solving that by multiplying and factoring. We've got x equals 0 and x squared minus 1 equals 0, which gives us the critical values of x, 0, 1, and negative 1. The x squared plus 1 equals 0 doesn't give us any critical values, and the x to the 4 plus 1 equals 0 doesn't give us any critical values. We can take each of these values of x, use any equation, and find the values of y that go with them. So there's our 3 critical points. Let's see how we use the second derivative test on those. We need to do the second partial of x and the second partial of y, and then the mixed partials. Now you can either do the derivative of this with respect to y, or the derivative of this with respect to x. You should get the same thing either way. Then use our formula. We multiply the second partials together, subtract the square of the mixed partials. We'll simplify that. So that is our discriminant. We will take one of the points, like 0, 0, and plug it in and see what we get. Now, if you have your chart handy, look at it. If the discriminant is negative, that tells us that that critical value is a saddle point. We take another critical value, in this case 1, 1, plug it into the discriminant, we get positive. Well, if the discriminant is positive, then we check the second partial. The second partial of x comes out positive. If the second partial is positive, we have a local minimum. The third critical value was negative 1, negative 1. We plug that in, we get positive. Since the discriminant is positive, we check the second partial. Second partial is positive. That tells us we have a local minimum. So those three agree with what I thought was going to happen from the original graph.